All right, let's get started. Welcome back to IDIS 343. Today we're starting chapter 3, inventory control when we're dealing with known demand. Now the word known here means we have full knowledge of what is going to be the demand, like per day, week, month, or year. We also call this scenario certain demand or deterministic demand. In chapter 2, we predicted demand. Here we ask the next question. Given that demand, how much should we order and when? Throughout this chapter, we'll be looking at the classification of inventory, the specific reasons a firm holds stock, and the well-known models like the economic order quantity, also known as EOQ, the finite rate production model, and the all units quantity discount model. All right. When we talk about inventory in a manufacturing or distribution context, we usually group things into a natural classification scheme based on value added. First, you've got your raw materials, the basic resources required to start production. For example, wood is a raw material for a furniture business. Then we have components or sub-assemblies, basically items that haven't reached completion but are ready for the next step. Like an engine waiting to go into a car. Next is WIP, that is work in process inventory. These are items actively being transformed. In a production environment, material is transformed to a finished good after many steps. For example, to make a bicycle, we need to weld the metal frame, then paint it, then put the seat on, and so on. While the welded frame is waiting for painting, and the painted frame is waiting for final assembly. Well, that's work in process inventory. The lean production approach, which we'll see later, is, obsessed with keeping WIP to a minimum to improve efficiency. Finally, we have finished goods, end items ready to ship out to the customer. The bicycle or the furniture basically is finished goods inventory. Well, you might wonder why we'd want to hold on to all this stuff in the first place, right? There are several big reasons. Economies of scale. When a business buys large quantities, they can get a better price per unit or lower transportation costs. Uncertainties. There are many uncertainties in the real world. For example, demand can fluctuate or, our supplier may not be able to deliver as usual. The book also mentions control costs. Sometimes it's actually cheaper to hold a larger batch of inexpensive items than to pay a worker to constantly monitor and reorder small amounts. Then there's speculation, stockpiling resources if you expect prices to skyrocket, and transportation or pipeline inventories, which are necessary when you have long lead times, like shipping oil from the Middle East. And of course, smoothing. We produce extra in the winter just to meet peak summer demand basically, without having to radically change our production rates or workforce. Alright, but inventory definitely has a dark side too. The investment in inventories in the US economy is enormous. We're talking nearly $3 trillion as of 2019. High holding costs are the most obvious. You're paying for space, insurance, and taxes. Then you have the risk of obsolescence, which is a huge deal in tech or fashion. Last year's smartphone is, basically worthless when the new model launches. And there's tied up capital. That money could be invested elsewhere, and cash flow gets, squeezed. All right, 3 more drawbacks. First, the risk of damage or spoilage. Fragile or perishable items lose value fast. Then there are demand fluctuations. If demand drops, you're stuck with excess inventory. And masking quality problems. This one is subtle but critical. When you have a massive buffer stock, quality issues stay hidden in the pile, making it much slower to identify and rectify defective parts. Companies that use scientific inventory control to solve these problems gain a significant competitive advantage in the marketplace. Every inventory model we study is defined by 4 main characteristics. Demand is the big one. Now, is it constant, the same value over time, like day after day? So we can use the EOQ model. Or is it variable, fluctuating demand? Is it known for sure? Or is it random, which we also call deterministic versus stochastic? Next is lead time, the time from placing an order until it actually arrives. Then there's review time. Is it a continuous review where transactions are recorded as they occur, like a modern supermarket, or a periodic review where you check at discrete points in time, for example, every Monday or the first of the month? Finally, how do we handle excess demand? Is it back ordered or is it a lost sale? Back order means customers are willing to wait to receive the order. You tell them, well, we don't have any today, but next Monday we can ship it, and they wait. This is, of course, costly, because your company needs to track these back orders and sometimes use expedited shipping to deliver on time. Lost sales means the customer just goes somewhere else to acquire the goods. Again, they might be happy to come back, so you only lost profit from one day, or they may never come, and then basically you've lost all future profit possibility from this customer. Now let's talk about the money. Cost minimization is essentially equivalent to profit maximization in these models. Three categories drive every decision. First, holding cost, what it costs to keep inventory on hand. Second, order cost, the cost to place and receive a shipment. And finally, penalty cost, sometimes called shortage or stock out cost. This is the price you pay when you don't have stock to meet a customer's request when it occurs. All right, now holding cost has four pieces. First, the cost of the physical space, like rent and racks. Second, taxes and insurance. Third, breakage and spoilage. And fourth, the most significant one is the opportunity cost of alternative investment. Money parked in a warehouse could be earning a return in, a savings account or a bond fund. For most companies, they need to earn an even higher rate called a hurdle rate to stay profitable. Now let's put some numbers on it. We define the annual holding cost per unit as H equals IC. Now capital I is the annual interest rate, the sum of our capital, tax and storage costs. Let's say that total is 37%. You should think of I as an annual inventory holding rate, because it's more than just interest. Lowercase c is the cost of a single unit, let's say $100. Then H equals 0.37 times 100, which is $37 per unit per year. If you held 300 of these items for 5 years, the total cost would be 5 times 300 times 37, which is, $55,500. You can also say if you buy something for $100 and keep it in inventory for 1 year, next year the cost of this item is basically $137, not $100 anymore. Well, that last calculation assumed inventory stayed fixed, but in reality, levels decrease as we satisfy demand and increase when new orders arrive. All right, so how do we compute cost when levels vary? There are two steps. First, we calculate the area under the curve described by I of t to find the total inventory during that time interval. Then we divide that area by the time interval, t sub 2 minus t sub 1, to find the average inventory. For the simple cases we'll study, basic geometry does the trick. Alright, so the familiar picture you need to remember is the sawtooth pattern. Imagine an order of size Q arrives at time 0, inventory jumps from 0 up to Q instantly. Then demand draws it down at a constant rate, which we'll call lambda, until it hits 0, then the cycle repeats. Now the dotted red line in the middle represents the average inventory, and because it drops linearly, it sits right at Q over 2. Now, alright, before we move forward, a quick refresher. Area of a rectangle is just width times length. Area of a triangle is 1/2 times base times height. That's really all the math we need to derive the core EOQ results. Alright, let's look at a single cycle. We have a triangle with a height of Q and a base of cycle time T. As we just discussed, the average inventory is basically the area under the curve divided by the time interval. Now, if we plug in our triangle formula, the area is 1/2 times Q times T. We then divide that area by T. The T's cancel out. And we're left with Q over 2, clean and simple. But what if the cycle length is different? Well, let's check. Now imagine a longer cycle. We have the same starting height Q, but the time axis is 2t, twice as long. Same logic, average inventory equals area divided by the time interval. Well, alright, if we plug in the numbers, the area is 1/2 times Q times 2t. Divide that by 2t and, everything cancels except Q over 2. Now here's the punchline. Cycle length doesn't matter. As long as inventory drops linearly from Q to 0, your average inventory is always basically half of your order quantity. Now let's try a quick check. Imagine a seasonal product where inventory peaks at 1000 units in July and drops linearly to 0 by December. That's a 6-month window. What is the average inventory for that second half of the year? Well, it's a triangle with a height of 1000, so the average is Q over 2, which is, 500. All right, same product, but now, what is the average inventory over the whole year? From January through June, the inventory was 0. The triangle area for the second half is still the same, but now we divide by 12 months instead of 6. That gives us an average of 250. I mean, the lesson here is always pay attention to the time window you're averaging over. All right, let's move to our second cost, order cost. Two pieces. You have the fixed cost, capital K, you often call the setup cost, which is, independent of the order size. When you estimate K, you should only include costs relevant to the ordering decision, like shipping or bookkeeping, not unrelated overhead. Then you have the variable cost, lowercase c, which is the per unit price. So the total cost for an order of size X is written as capital C of X equals K plus CX. All right, well, the graph makes this very clear. At X equals 0, the cost is 0. But the moment you place an order, the cost jumps to K. From there, the line rises with a slope of C. That jump at 0 is the key. I mean, it costs the same fixed K to order 1 unit or 1,000, which is basically why we don't place tiny orders constantly. Finally, we have penalty cost. This happens when you can't satisfy demand. If it's back ordered, the customer waits and you pay for bookkeeping. If it's a lost sale, you lose the profit. Either way, you face a loss of goodwill cost, which measures customer satisfaction. Now, since demand is known and constant in this chapter, we can plan perfectly, So we're actually going to ignore penalty cost for the EOQ model we're about to study. All right, that covers the fundamentals of inventory classification and costs. Next time, we'll dive into the math and derive the actual EOQ formula. Thanks, and gig 'em.